Good afternoon, everyone. I hope I can be heard.
Yes,
So
sir.
today we will, thank you very much. Today we will look at single view geometry. When you just have one camera, how to measure things and how other parameters can be computed. And then we will look at the second part of convolutional neural networks. Mm, So that is the plan for today. So we briefly look at camera calibration using vanishing points and measurement from a single image and applications of the single view methodology. So when you have images taken from several cameras, so several viewpoints, our final intention is to make a 3D reconstruction like that of the scene. So what we know that using a 3D reconstruction from a single image is not possible, but under some conditions, we can attempt that, considering the parallelism of lines, perpendicular nature of lines in the scene, and so on. So now there are many applications like that. If you go to this link, which I will show you later, by considering that this is a rectangle and so on, we are able to make a 3D reconstruction of this. And in this special video, they have been able to keep artificial billiards and so on. Yeah. So if the coordinates of the reference 3D points are not known, we can use the scene features such as vanishing points to estimate something about the cameras. So what are those things? Before that, we looked at the cameras last time. So we know that this is the intrinsic camera calibration matrix. It is a 3 by 3 matrix. Uh, and this was done 2 weeks ago. This is the rotation matrix. It is a 3 by 3 matrix. It's a 3 by 3 orthonormal matrix. It's a special matrix. This is a 3 by 1 matrix, or it is a 3 by 1 vector. Therefore, together R and T form a 4 by 3 by 4 matrix. And X, because we add one last coordinate, 4 by 1 matrix, as you can see here. And X is are the image coordinates up to a certain scale. It is a 3 by 1 matrix. So this is that nature. So we looked at camera calibration using a calibration object last time. And that means when the 3D points are available in 3D coordinates in meters and the image coordinates of those points are available, we can attempt to make a 3D reconstruction. But today, we will look at how to do that using so-called vanishing points and vanishing lines. Now, one thing that is true in an image is, although the lines are parallel in the real scene, you know that these lines are parallel in the real scene, right? In the image, they seem to be meeting at a certain point, and that point we call vanishing point. So this uh, family of lines will have vanishing point. This family of lines will also have a vanishing point. Both of them are finite and we can locate them somewhere here. But this family of lines, they are still parallel. They will have vanishing point at infinity. And when you join two vanishing points, the light blue line, we call it the vanishing line. Okay, so let's mathematically characterize this briefly. Think about this as the image plane. This is the camera center, and this is a line on the scene. And we take a point on the line on the scene, and if we join that point, this is a point in the 3D, and if we join that point at the camera center, and when it cuts the image plane, we have the image. This is the image point, right? Small x. Now what we want to do is slowly move this capital X along this line in the scene, like so. So when you move it, you can see that the image point reaches a certain limiting location. So you can move further, and finally you move it to a line that is parallel with the scene line, and that is it. This is the last point where this uh, point on the image would move. Now that one is called the vanishing point. So this ray is parallel to the line on the scene. So we can parameterize this concept. So let's take x naught as one of these points. X naught is this point. X naught, Y naught is Z naught 1. And direction vector D1, D2, D3 is that direction. So you know that the direction can be written as a vector, right? So if you take X, Y, Z axis, you know that we can write them as a direction. So like so. So if this is x and if this is y and if this is z, and we know that x-axis we can write as 1, 0, 0, right? That's the direction, and so on. Remember, we write one more coordinate here. Forget about that for the time being. So this is the direction, right? Okay. So what we can do is xt. We can write any other point on this line, along this line, xt, this one, by writing t times d1, t times d2, and t times d3, because this d is a direction. Now the trick that we do is we divide this by small t. We divide it by small t. You can see that this d1, d2, d3 is there. Now, how can I send this point to infinity? You can send that point to infinity by setting t to infinity, right? T equals infinity. When you set t equals infinity, you can see these things will become 0, and what you have is d1, d2, and d3. And then finally, this last coordinate becomes 0. So this one we call a point at infinity. So as you can see, this point which is at infinity is also represented using 4 coordinates, homogeneously represented as any other coordinates. That's why these are called homogeneous coordinates. Okay, so a point at infinity is a direction d1, d2, d3 in that direction. So x infinity is the point at infinity, and if we take an image, that can be finite, as you can see in this diagram, right? I mean, okay, this point is at infinity, but its image is right here. It's finite. So this is V equals, this is the imaging equality. There's a scaling factor, P infinity. So these are those vanishing lines and vanishing points. You can see in different directions the vanishing points they have written. V1 and V2 are finite vanishing points, and V3 is an infinite vanishing point. So we can align the world coordinate system with these directions. So now let's see how camera calibration can be done. I will give you the idea, and I will not go through all the details here. Now, as we remember, the camera calibration matrix is a 3 by 4 matrix. There are 3 columns and 3 rows and 4 columns. Okay, let's call them P1, P2, P3, P4, the columns. Now, let's take this direction. This is your x direction, right? X direction. So this is the point, the x direction of the point at infinity in the x direction. Now, if you do this multiplication, you can see that P11 multiplies with this, P12 multiplies with this, P13 multiplies with this, P14 multiplies with this. So what remains is only P11. In the second equation also, you will get the same effect. P21 will remain, all others will become 0. P31 will remain, all others will become 0. So this is the vanishing, this is the point at infinity. Therefore, when you take an image, it must be the vanishing point in x direction. So this P1 is the vanishing point in x direction. Then take the next one. This is the y direction. So you know that you can get P2 here. P2 is the vanishing point in y direction. And then P3 is the vanishing point in z direction. It is that simple. But unfortunately, we can see that although we get them as vanishing point, there is a problem. That problem is these P1, P2, P3 that we estimate as V1, V2, V3 are related by an unknown scaling factor. This unknown scaling factor is the problem. So therefore, we cannot fully recover the camera matrix like this. So this one is the P4 is the image of the world origin. This is the origin, right? 0, 0, 0, 1. Yeah. Projection of the world origin. Problem, this only gives us 4 columns up to independent scale factors. Additional constraints need to be are required to solve them. But there are additional constraints. Those additional constraints are that these directions are perpendicular to each other. Now, if you take E1, E2, E3, you can see E1 is the x direction, E2 is the y direction, E3 is the z direction. Because they are perpendicular, you can see that if you get the dot product between them, they are 0. Even when you look at it right now, you can see that. Because if you multiply, if you take E1 dot E2, E1 dot E2, that's equal to 1 times 0, right? Plus 0 times 1 plus 0 times 0, right? That's a dot product. You multiply individually these things and you add them. That's how you get the dot product. You can see that this is 0. What that means is they are perpendicular. So we can take orthogonal directions in the image and apply this constraint. We know that V1, the vanishing point is when you have the camera matrix, this is P, and E1, EI0, so one of these things, EI, one of these things. Uh, so we can put EI here without a problem. T vanishes. Uh, we can obtain E by taking the inverse of this. So when you take the inverse of this, K inverse has to be obtained. Inverse of the R is R transpose. That is the nature of an orthonormal matrix. So we have a formula for EI, and we know that these are perpendicular, so we can impose this condition. EI transpose times EJ is 0. So this one transpose times this one must be 0. This one transpose this one must be 0, and so on. So when you impose these constraints, you get R and R transpose in the middle. R is the inverse of the R transpose. So here you will get the identity matrix. So here you will have this important relationship here. Vi transpose K inverse Vj is 0. So extrinsic parameter matrix, that means the rotation matrix disappears, and we are left with the constraints on the calibration matrix. So you can see at once a constraint on the calibration matrix is available if you know the vanishing points. So this is how many constraints do we get? So 3, 1 for each pair of vanishing points. Then how many unknown parameters does K have? F, Px, and Py. So therefore we can obtain that. A couple of complications. The constraints are non-linear, but it is not hard to do the algebra. At least 2 finite vanishing points are required to solve for both focal point and the principal point. This can be solved if you have 2 finite vanishing points or 3 finite vanishing points. In this case, it cannot be solved. Like a whole wave condition like that, it cannot be solved. But in this case and in this case, it can be solved. So now we have constraints on the vanishing point. Because of that, we can solve for K. And then we have to solve for R. So now we have K inverse Vi equals R EI. Now we have found K. Then we consider this R as R1, R2, R3, the columns. So we get R1, RE1 is R1. Thus Ri is K inverse Vi. So like that, we can find the R's also. The scale ambiguity goes away since we require Ri squared is equal to 1 because R is an orthonormal matrix. So I know that this is a little bit complicated, but from this what you can see is we can use a calibration object and find the images of that and do the camera calibration and obtain the K value, R value, and the T values, R values, and the T values. Also, if you know 2 finite vanishing points, still we can obtain that. So people have done these things to automatically calibrate the camera using these kind of constraints. So that is all we have to know. So solve for implicit parameters, focal length, principal point using the 3 orthogonal vanishing points. Get extrinsic parameters, that means the rotation, directed from the vanishing points once calibration matrix is known. This is how you do that. Advantage, no calibration chart or 3D, 2D correspondences are required. This could be completely automatic. This advantage only applies to certain kinds of scenes. It is tricky to accurately localize vanishing points. Need at least 2 finite vanishing points. So now let's briefly look at measurements from a single image. This is also an interesting thing. Let's see, when you have a camera and an object of which you know the height, how you can do a measurement. We did a small example of how you can do a measurement when the camera axis is perpendicular to the scene last time. And when all the camera parameters are known and distance from the camera to the scene, camera lens to the scene is known. We did an example last time. But this time, we will not make those assumptions, but let's do that. So measuring the height, measuring within planes, all these things are possible with that. So this is a funny example. If you like, you can go to this link and see what this is. It's called Amy's room. Okay, so this is the problem that we are considering. There is a calibration object in the scene. Okay, maybe you have a pillar, and then on pillar a meter ruler is pasted. Now, when a person is walking about, is it possible for you to know the height of that person when the person is not near the pillar? If the person is standing against the pillar, of course you can find the height. But when the person is far away, you can do that. So the trick is interesting. The trick is knowing what are the parallel lines. Yeah. Okay, let's do this. Now let's draw a line from the bottom of the calibration objects of the ruler through the leg of the person. Okay. One thing is, assume that this is a tile floor. In this tile floor, you can see one set of parallel lines, these lines, and another set of parallel lines, these lines. These are parallel. Those lines will seem to meet at some place here. The other set of parallel lines will seem to meet at some place here. And the line joining them is called the line at infinity or the horizon. That's the horizon. That's the horizon. So if we actually look at an image of two railway tracks, which are parallel lines, okay? Let me show you an image. So I just typed railway lines. You can see these two lines, they meet at the horizon, right? Railway tracks, you know, are parallel, right? They meet at the horizon. So anywhere it's the same. See, can you see that? They meet at the horizon. Horizon is a place where sky touches the earth. Can you see that? Parallel lines. This is true. In any direction, this is true. See? Can you see that? This is exactly the horizon, right? That's where they meet. Here, see? Beautiful, right? It's a beautiful thing. Here, see? Right. Okay. So that's what we are saying. So you draw a line here to the horizon, and then this line will go and cut the horizon somewhere, cut the horizon here. And from there, you draw another line touching the top place of the person and find where it touches the ruler. It touches the ruler right here. Okay. I'm asking you this question. What can you say about these two red lines, this line and that line? What can you say about this line? So I'll post a little question to see whether you can answer.
Are they at 45 degrees?
When you look at the image, you see that they are 45 degrees. But think about the horizon. What kind of lines meet at the horizon?
The focal point?
Okay, now let's take parallel lines on the image. Okay, so these lines are parallel. Right? This is parallel. Think about tile flow. They are parallel lines, and these are parallel lines. What happened to those parallel lines? They meet. They meet where? They meet at the horizon. That's one family of parallel lines. Take another family of parallel lines. These are parallel lines. These are parallel line. These are parallel line. These parallel, parallel, parallel. That family of parallel lines, they are parallel to each other. Where do they meet? They meet at the horizon. Okay. Now these two red lines, they also meet at the horizon. You can clearly see that. That's how we drew it. Now what can you say about those two parallel lines? Okay, I gave the answer by a mistake. They are parallel. These lines are parallel. That's the amazing thing. Although we see it as meeting here, they are meeting at the horizon. That means they are meeting at the infinity. So they are parallel lines. If they are parallel, that means this person's height must be 5 feet. and 2.5 inches. That many inches. I think 5 and 3 inches. That's the height of this person. Exactly that much. Yeah. So if you are able to take an image of a person walking by, when you have the ruler pasted on the post, and you have to set of parallels, that means you can identify the horizon, you can find the person's height. So this is using measuring with a ruler. There is a ruler in the scene. Yeah. So this is one way of measuring. But the other way of measuring, okay, so the height of the turtle also you can get 2 feet. Camera, this is the camera height. Camera is at that height. There is a way to measure without a ruler also. That part I will not discuss. It will involve some equations and so on. But one thing that you need to know is that is also possible if you have a calibration object. That means if you know that this is a reference object of which the height is known, then it is possible to find the height of an unknown object. Yeah, so I will skip that part. This is done using a thing called cross ratio. I will not expect you to know that. But these things are interesting things. Yeah. Okay. So using this concept, if the reference is like this, you can find the height of this person and the height of this person and so on. So height in this old scene can also be found. Compared to the height of Christ, what are the heights of these people? So if you want to do some measurement on a plane like this, you know that this plane is not perpendicular to the camera's optical axis, then you have to rectify it, unwarp it, and then only you can do a measurement. Otherwise, the measurements are incorrect. Then you can measure. What kind of a warp is this? This is called a homographic warp. So homography. And we have studied what the homography is. So if you want to unwarp that, you can click 4 points here, click exactly the same 4 points here and find the homography between them and then unwarp. So these are the things that people have done in 2000, making a 3D of that. So people have used these simple techniques to obtain a 3D pop-up using a 2D image and so on. And this application is because they have some notion about the 3D nature of the scene, they were able to do detections, avoiding finding people at treetops or something. Sometimes the detectors make mistakes. They find people on treetops, but you can avoid them because you know the geometry here. So you can eliminate these incorrect detections. So this is the video. I'll show you what this application they have done. It's quite beautiful. You can see by estimating the 3D nature using these lines and so on.
In this video, we describe a technique for inserting objects into images without requiring access to the scene, multiple photographs, special equipment, or any other aid. Here, a synthetic glowing sphere illuminates the room, reflecting in mirrors and casting shadows. Our method allows for objects to be inserted with proper perspective and occlusion, and relit with an estimated lighting model of the scene's illumination. Inserted objects fully interact with the scene. This dragon casts red light onto the brick beneath it. In the background, the bottom of the sphere is receiving a slight red tint from the light striking the brick below.
So you can see they are able to insert 3D objects and so on because they estimated the scene geometry. Yeah, you can have a look at it. I will upload the slides. I have not uploaded the slides, so I'll quickly upload them. Sorry about that. Sorry about that. Not uploading slide. Okay, so that is about a single view. Now I think you understand about the camera and the camera parameters, the focal length, principal point, how to estimate them, and how to make measurements using cameras. When the axis is perpendicular, it's very easy. Otherwise, when object is placed with a calibration object is possible, and camera calibration, the direct method, as well as using vanishing point method, you understand. Now let's look at the epipole geometry. When there are two cameras, how are these two cameras views related to each other? Okay, so this is what we are going to study. We are going to study when now this is camera center O of the first camera. This is the camera center O prime of the second camera. And this is the image plane of the first camera. This is the image plane of the second camera. And the line joining the two camera centers we call the baseline. That is actually the line joining our two eyes or something. For us, for human beings, the baseline is about 5 centimeters, the distance between the two eyes. That's called the baseline. And the baseline cuts the image plane at 2 points, the first image and the second image. We call them epipoles. And E and E prime are the symbols, standard symbols used for that. Okay. Then there is a 3D scene and there is a capital X, a 3D coordinate in the scene. Our question is, where does this image appear in the first image? So you can clearly see in the first image that scene point X, yeah, it can be here, 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 or anywhere along that ray. The image is for sure at this location. That's where this ray cuts the image plane, the ray from the camera center to the 3D point. That's where the ray cuts. That's the image on the first camera. Now, one thing is we do not know, although we know the image, we do not know where the 3D point is. 3D point can be anywhere on that line. That is the action of a camera. Anywhere, any point on this line will be imaged at this point. So therefore, because we do not know where this point is along this ray, in the next image, in the second image, it can appear anywhere on this line. This line is the image of that ray. Again, this line, this red line, is the image of the ray that is going to the camera center of the first camera. Image of that ray. Can you see that? So the image of capital X, which you do not know where, we do not know where it is, right, can appear anywhere along that line. Anywhere along that line. So anywhere along that line, right? So that line is called the epipolar line. This is what we are going to study in this lesson, and we want to mathematically characterize this and identify two special matrices. One is called the essential matrix, the other one is called the fundamental matrix. When we know about the camera poses, that means the location and the orientation of the two cameras, we can obtain the essential matrix, and if we do not know those also, we obtain the fundamental matrix. It is so important, that's why it's called the fundamental matrix. So we will look at the epipolar geometric setup. I will explain this setup again to you and come up with epipolar constraint, essential matrix, fundamental matrix, and briefly how to estimate the fundamental matrix. Okay, here again the geometry, we will go step by step. I hope you are ready. Okay, so you can see O and O prime. Again, O is the center of the first camera. O prime is the center of the second camera. And the line that joins these two centers is called the baseline, line connecting the two origins. And epipoles are where the baseline intersects the image plane or the projections of the camera in each of the views. And consider a point X, capital X, with projections small x and small x prime. So this plane joining O, O prime and capital X is known as the epipolar plane. When we change capital X, you can see this epipolar plane rotates about O and O prime, about O and O prime. There is a family of planes passing through O and O prime. Epipolar lines connect the epipoles to the projection of X. Equivalently, they are intersections of epipolar plane with the image plane, thus they come in matching pairs. So you can see this beige color plane, yeah, beige color plane, this plane, that plane intersects the image planes, right? Those are the two lines at which they intersect. These are called epipolar lines. So you can see the geometry again, epipolar plane, epipolar lines, baseline, and epipole. Okay, so these are actual epipolar lines drawn on an image. So this point, this is the epipolar line. The corresponding epipolar line actually goes through that point on the image, in the next image. So consider this point, the corresponding epipolar line actually goes through that point in the second image. Okay. So when the two cameras are at different configurations, epipolar lines appear in a certain way. So when the cameras are sort of converging on an object, both the cameras are looking at the same object, epipolar lines look like this, emanating from the epipole, which is, for example, here, and for example, there. But when the cameras are parallel, optical axes are parallel, epipolar lines are horizontal, like this. They do not meet at a finite point. They meet at infinity. Epipoles are at infinity, like so. This happens when you keep a camera toward a scene while traveling on a train or something. This is moving along the axis of along the corridor like this. Can you see that? Like this. I hope you can see the change when I'm moving back and forth. Then the epipoles are like that. Focus of expansion kind of epipole lines. So these concepts can be used to simulate videos also. Simulate that you're walking along a corridor. Okay. So we looked at the epipolar geometry setup. Is there any question about the epipolar geometry setup? Please feel free to ask questions. You're most welcome to ask, and I'll be very happy if you ask a question to answer. Okay, we'll move forward. Epipolar constraint. Okay, now let's capture that mathematically. Suppose we observe a single point X on an image, and this is the ray. Where can we find X prime corresponding to X in the other image? That's the question. Yeah. Okay. So where can capital X be? It can be here. Capital X, that means the point in 3D that gave rise to this image small x. It can be here. It can be there. That's also a possible location. It can be here. That's also a possible location. It can be here. That's also possible. Anything on this ray is valid. any point along this ray, I'm not properly drawing that ray, this is that ray is valid, right? So therefore, the corresponding image on the other camera can be anywhere on the image of this ray. That image of this ray is this line joining E, going through E. That's where the epipolar plane, this epipolar plane, cuts the image plane. So like this. That's called the epipolar line. Along the epipolar line, corresponding X, projection of visual ray connecting OX with the second image plane. Where can we find X prime corresponding to X in the image? Along the epipolar line. Corresponding to X, projection of the visual ray connecting O and O prime, O and X in the second. I hope you understand that. I will show that again. So consider this ray. This is the ray, right? This is that ray. This is that ray we are talking about. That ray is projected here in this other image. So that is the place. That is the line. Okay. So similarly, if you know that this is your image on the second camera, where does this point can be? It can be here, 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 or anywhere along that line in 3D. So therefore, image of this line in the other camera is the place where X's image can be there in the second image, here or here or here or here, anywhere along this line. That's the epipolar line. Okay, so we have a special symbol for that. We call it L prime, the epipolar line here. We call this L. Yeah. So you can see the epipolar lines, actual epipolar lines, corresponding to this point. This point should lie on the other image anywhere along that line. So you can clearly see it is exactly there, right? This point should lie anywhere along the epipolar line. So that has been true. It is here, right? Take this point. It must lie along this epipolar line. So truly, it is here, right? Along that line. That's the thing. Okay. Do you have any questions about the epipolar line? You can mathematically find them. Okay, let's move along. Whenever 2 points X and X prime lie on the matching epipolar lines L and L prime, the visual rays corresponding to them meet in space, that is X and X prime could be projection of the same 3D point. Yeah. It is generally not so. Two lines in 3D do not meet. So here these two lines don't meet. They go like that. They don't meet in 3D. So I'll show you something. So they do not meet in 3D. Usually they do not meet in 3D, but they meet under certain conditions. Yeah, they don't usually meet. So caveat, if X and X prime satisfy the epipolar constraint, it does not mean that they have to be a projection of the same 3D point. So they can be along anything, anywhere, right? Along the ray, right? It can be here, this can be there. It doesn't have to be exactly here. That problem is there. Okay, epipolar constraint is that. Now let's mathematically characterize that using the essential matrix. Okay. All right. Now this is the slightly mind-mongering point. Okay. So now let's consider this epipolar geometry. Capital X is there. It's the 3D point. Its image on the first camera is small x. Its image on the second camera is small x prime. T is the translation between the first camera and the second camera. That is, this vector is that one. And R is a rotation. This is the vector x prime. This is the vector x. Okay. R is the rotation of the camera O prime with respect to the camera O. T is the translation of the camera O prime with respect to camera O. Assume that intrinsic and extrinsic parameters of the camera are known. World coordinate system is set to that of the first camera. Then the projection matrices are given by KIO. Now, if the intrinsic camera calibration matrix, the 3 by 3 matrix, focal length principal point is K, Then this is aligned with the world coordinate system. So it is the first matrix is the identity matrix. There's no translation, so translation is 0. This is the camera matrix for that. So remember our camera matrix B is what? K RT. ART. This is what we studied. Okay. Second camera, let's call it K prime RT. Okay. So we normalize these pixel coordinates with multiplying by K inverse. This one also multiply with K inverse, K prime inverse. So you have I0x and RTX. Take the K to the other side. Okay. So normalized coordinates, X norm is this one, X prime norm is this one. Then consider this. How do we, if we know capital X, consider that as small x, these are 3 numbers and 1. And this is the camera. How do we get the normalized ones? Okay, remember Px, that's all, right? Px is how you make the camera image. So this is capital X, so you do it. For this, it is RTX1. So this is Rx times T, right? Rx times T. So small x prime is Rxt. Small x is x. Okay, and T is here. What can you say about these 3 vectors? Vector x, vector 3, and vector x prime. So let me ask a question.
Size is the same, but the direction is 90 degrees opposite.
90 degrees thing we do not know, but what we know is they are on the same plane. Do you agree with that? They are on the same plane. They are on the same triangle.
Correct.
They are on the same triangle. Okay, now I'm going to invoke on a theory that you perhaps have done for A-levels. Not perhaps, you did that for A-levels. Okay, this is that theory, okay. That theory is this one. If you have a vector A, okay, and if you have another vector B, B, and if you have another vector C, is C, do you remember how to get the volume of this parallelepiped? The volume of the parallelepiped is obtained by C dot A cross P. C dot A cross P. Yeah, this is called the triple scalar product, I think. I think you triple scalar product. Yeah, this is this thing, triple scalar product. So yeah, this one. So perhaps you remember that. This is the volume of that. But in this situation, you can see that all the 3 vectors are the same plane, right? All the 3 vectors, this T vector, this X vector, and this X prime vector are on the same plane. If they are on the same plane, the volume must be 0. The volume must be 0. So therefore, this product must be 0. This gives the volume. So that's the theory we are going to invoke. So we have x prime is equal to rxt. This means that the 3 vectors x prime, rx, and t are linearly dependent. These constraints can be written using the triple product. So x prime t cross rx x prime t cross rx is equal to 0. X prime t cross rx is equal to 0. This is the relationship. So we write this as x prime transpose tx. Tx is a matrix that affects the cross product times Rx is equal to 0. This is called the skew symmetric matrix. Skew symmetric matrix. So this is how you do that if you have capital A. So if A has elements A1, A2, A3, A1, A2, A3. It's the skew symmetric matrix is like this. So think about the skew symmetric matrix is using that skew symmetric matrix, you can get the cross product by matrix multiplication rather than using the cross product formula. So this is what it is. So therefore you can see x prime transpose, we use a special symbol E or the essential matrix X, and that essential matrix is T Q symmetric matrix times R. This is your E. That's the formula for that. So this is called essential matrix due to Longet-Higgins, 1981. It's a very important discovery. So x prime transpose Ex is equal to 0. So this is the essential matrix. It's a 3 by 3 matrix. So 2 points correspond to each other if they can be captured into this x prime transpose Ex relationship. This is all you have to remember. X prime transpose Ex is equal to 0. Okay. So recall, yeah. So other things I will not go through. So there are relationships for L prime, L, that means equations for the epipolar lines given x and x prime. There are equations. I will not go through them. It's a singular rank 2 and has 5 degrees of freedom. Yeah, that's the essential matrix. Now let's look at the fundamental matrix. Okay, fundamental matrix. So the essential matrix we computed using the normalized coordinates. That means multiplying the x's and x primes by k and k inverse respectively. So like so. But if we do not do that, and if we have non-normalized ones, that means into this we substitute this one, into this we substitute, I'm sorry, into x norm we substitute this one, into x prime norm we substitute this one, we get the fundamental matrix. So the relationship between the fundamental matrix and essential matrix is this one. So fundamental matrix is for uncalibrated point, unnormalized point. Fundamental matrix. So it is very important. So we have to remember this. The fundamental matrix x prime transpose fx is 0. F11, F12, F13, and so on. It's a 3x3 matrix. Let me give a small. We take an example. I'm trying to look for that example. What we do. Let's do this problem. I hope you're ready. Figure Q3b shows a 3D point X and two camera matrices, cameras C and C prime. The cameras are separated by a distance B. The point X is projected to the image plane of the cameras X and X prime. Mark X and X prime. Where is X? X is the image of camera C, right? So this is the X. This is my X, right? Where is X prime? So I had to project a ray from X to the next camera C, right? C prime. So project a ray like that. Cast a ray like that. So please assume that this is a straight line. I could not draw that as a straight line. Let me try again to draw a straight line. There's no way to draw a straight line. Okay, let's be satisfied that there's a straight line. So this is my X. That point. And this point is my X prime. Okay, that's the first question. If X is not known, but X is known, mark the possible locations of X prime. Can you think about it? So in the second question, we are trying the second question now. This one. X prime is not known, so we do not know that. But X is known, that means we know that X is here. Mark the possible locations of X prime. We have to mark the possible X prime. So think about it. Okay, because we do not know capital X, that means we do not know where this is. What are the possible locations of that? We know that possible locations are along that ray. Anywhere along that ray, the capital X can be. So therefore, the projection of that ray on C prime are the possible locations of X prime. So therefore, for this question, you should draw the epipolar line. This epipolar line, this is the epipolar line. This is the possible location L prime. Okay. Mathematically express constraint that relates X and X prime. So these are cameras, and we have not been said that they are calibrated. So therefore, we have to go for the more general one. That is the fundamental matrix. So relationship is X prime transpose F X is equal to 0. Okay, but a hint has been given, right? The fundamental matrix is given. Fundamental matrix is given. The point pairs are x1, x1 prime, x2, x2 prime, x3, x3 prime are given. It's asking determine which pairs satisfy the equivalent constraint. That means we have to put these 2 points along the fundamental matrix and see which ones result in 0, right? That you should have a calculator, but I will do this on VS Code. Okay, let's open. Okay. Let's solve this problem. All right, first of all, import numpy as np. That. Okay. So now let me write f equals np dot array. So I had to copy this. Without being lazy, I'll do that. 0, minus 0.0005, 0.03. I hope that's okay. And next one is oh my goodness, it knows sort of what I'm typing, right? 0.0005, 0.0 minus 0.08. That's the next one. And then finally, minus 0.04, 0.09, 1.0. That's a fundamental matrix. And we can print it. So we have it, right? I hope it is correct. Okay. So now let's get the first pair of points. X1 is equal to, in the array, we have to carefully write that. First point is 69.18. Then y coordinate is 74.19. Then 1. Okay. That's fine. That's the first point, x1. Then x1 prime, let me call x1 prime, equals np dot array 75.91, 96.27, 1. Okay, that is it. So now I can compute the residual. I can print x1 prime transpose times f times x1. That's the equation, x1 prime transpose fx. So let's see how much that is. So it's 0.002. So we don't know whether it's small or not because we do not know the other values. So let's get the other ones also. X2 NP array, and let's put these numbers in 11.04, 43.59, and 1. Then X2 prime, 34.64, 63.98, and 1. Okay, so let's get that also running, and we can print that. It's 0.004. It's much smaller, right? Can you do the last one? So I'll give you some time. Please do the last one. It's so easy. You can see the screen. So please do this. I'll drink some water and come. Okay, I hope you got the answer. So let's do the last one also. X3, 71.34. $39.43 and 1. X2 prime, X3 prime, 31.59 48.22 and then finally 1. So let's write that equation X3 prime transpose if in that. So you can clearly see this is quite large in magnitude. These two are small. So X1 and X1 prime, X2 and X2 prime are compatible. X3 and X3 prime are not compatible.
So is there any significance having the two brackets in the final answers?
Here, this is because it's a product between matrices. That's why it has this. Yeah, because it's a product of two-dimensional matrices. That's why.
Okay, sir.
Yes, there's a significance. Consistent and x2 and x2 prime. Okay, x1 and x1 prime are consistent. X2 and x2 prime are consistent. X3 and x3 prime are not consistent. So because I gave you an inconsistent one, you know the others are consistent. Otherwise, you don't know with what threshold you should compare. That's the answer to this question. I hope that now it's clear how to find the consistent points in the fundamental matrix. That consistency means the second point is found on the epipolar line. So here's the solution, right? That's the solution. We can even write these things if you like. X1 prime transpose X. I made a slight mistake in this calculation because I had to get x1 prime transpose and yeah, that's correct. It's correct. X1 prime transpose is x1. Yeah, that's what we get, right? This one is what I have written is x2 prime and x2 prime transpose. X2 prime transpose and x2. And then finally this one is x3. Okay. So that's a fundamental matrix thing. I hope it's clear. Yeah. So we use this relationship and an example. So F has 7 degrees of freedom, and there's a way to estimate the fundamental matrix, but I will not go through about this in too much detail. So you match these points, and you have matching points, and you write matrices, and then there's a way to estimate that, but I will not go through that. Okay. Then let's briefly look at the structure from motion. But yeah, let's look at the structure from motion the next time. But I will go through the rest of the convolution neural networks first. So as I described last time, we want to do these two things on the same day because these convolution neural networks, they also need some time to understand.